So Unit 6 from Jan 2022, we did first two questions and question 3 and 4. In question 3, we have a radioactive source is there. A radioactive source which is emitting out beta and a gamma radiation, and state two precaution that should be taken when using a radioactive source. So when we are using a radioactive source, what are the precautions we should take? First thing, for more accurate result or accuracy of the like normally it's about the safety precautions are they related to the radioactive source. So what are the safety precautions? We should maintain a distance from a source or keep the source in a lead line box and use a source for a short period of a time. Like these are the safety precautions. Use lead, like keep the source in a lead line box. So we should keep the source in a, these are the safety precautions related to a radioactive source. So we should keep a source in a lead line box and use the source for a short time. And we should maintain or keep distance from the source or use long forceps to handle the source. In 3B, the radiation emitted from a radioactive source can be investigated using an apparatus shown. The GM tube detects the beta radiation and gamma radiation, as you can see, a radioactive source. A rate meter displays the count rate from all radiation detected from the GM tube. Explain why the background rate should be measured. Whenever experiment is done related to radioactivity, we should always correct for background. So background rate should be subtracted from the, because background rates are leads to, if we don't calculate, then it will be a systematic error. Systematic error means like always you will get a higher value. Like always, if it was a random error, you can get higher value or you may get lower value. But every time, if the background radiations are there, you will get higher value than the actual one. So it is refers to a systematic error. So why the background count rate should be measured? Because the background counts leads to systematic error. And what we should do, we should, the radiation from the source can be calculated by the total minus the background. So the total radiation which we receive minus the background radiation will get the radiation from the source. So background, like for example, whenever an error is there in the experiment and it always a sustained, like it is continuous error is there, and you always get either a higher value or either a lower value, then it is referred to systematic error. So in this case, like example, zero errors is also a systematic error. If there's an error, always either you will get a higher value or you will get a lower value. But in a random error, what happened? One of the result might be higher, one of the result might be lower due to a sudden change in condition. So if from a graph, how you can identify, sometimes they ask from the graph that estimate it's like it's having a random error, systematic error. So how you can identify if you find that the values which you are getting are higher than the pattern. So what it gives an idea, it gives an idea that there's a systematic error. Same thing, the value which you obtain are lower than the pattern. It's also systematic error. But if the values are spread out, then it will be a random error. So that's how we identify systematic and random error from the graphs. The corrected count rate varies over time according to a relation. The C naught is the initial count rate and lambda is a decay constant. Explain how a graph for ln C against T could be used to determine the value of lambda. So what you have to do whenever, like this is a main equation, C is equals to C naught e raised to power minus lambda T. What we'll do, we'll take ln both sides. So this will be ln C and this will be ln C naught e raised to power minus lambda T. Whenever two quantities are multiplied, we write them in addition. So we can say ln C is equals to ln C naught plus ln e raised to power minus lambda T. Remember in ln or a log, when two quantities are multiplied, we write them as a sum. So ln A plus ln B. Then ln and E are anti-function of each other. They cancel out each other. So we are left with ln C is equals to ln C naught minus lambda T, like the whole power. What power is written? Say x is there, ln e raised to power x is equals to ln, it equals to x. So same thing, it's minus lambda T. If I rearrange the equation, so I can say ln C is equals to minus lambda T plus L naught, ln C naught. Or I can also say ln C is equals to minus T, or I can compare now with the equation of straight line using a y is equals to mx plus c. So on y-axis, if I plot ln c, and on x-axis, because we are using a formula y is equals to mx plus c. On x-axis, if we have t, so what will be the gradient? The gradient will be equals to minus lambda. And the y-intercept, so it will have a negative gradient, and the y-intercept is representing ln. See, so the shape of a graph, because lambda decay constant is there, and in a negative gradient, a constant. So this is a negative gradient, and this y-intercept represent the ln C naught. So the graph, how we can determine lambda, the gradient, negative of the gradient will be equals to lambda. Then the source contain two radioactive isotopes X and Y. The table below shows the corrected count rate for an isotope decay. Plot a graph for LNC versus time on opposite grid. View the additional column to record the. So what we have to do, we just have to take LNC here, and the unit will be second inverse, and just take ln of this one. And write the answers, and then you have to plot a graph the next, like ln 633, ln 217, ln 167, ln 140. So you will write in this column and then plot a graph between t and lnc. And the shape of the graph, because here is a graph which you will plot, the shape of the graph will be so on y-axis if you have lnc, on x-axis you have t, as it is a constant gradient, so you will have the values like this. For as the time is increasing, the value of lnc is decreasing. So to work out this maximum, like beginning count, this y-intercept will be equals to ln c naught. And the gradient, when you take out the gradient, the negative of the gradient will be equals to minus lambda. So lambda, you'll get the value for a lambda as positive. So these two parts, the isotope X has a half-life of 30 minutes. Determine the lambda in R for isotope Y. So how we can determine the half-life of the isotope? For this part, because we have to plot a graph for LNC and use an additional. So this is a graph for like the source containing two isotopes X and Y. Table below shows count create for isotope which have decayed. And isotope X has a half-life of 30 minutes. And then we have to determine the value for lambda in R inverse for isotope Y. So as we discussed, like the equation that the gradient is actually equals to the lambda. So what you have to do after plotting a graph, you have to take a gradient, and that gradient will be equals to lambda. So plotting a graph, taking a gradient, and that will give us the value for lambda. And the last part, hence determine the half-life time for isotope Y. So isotope, and they already mentioned here, the source contains two radioactive isotopes are there, X and Y. So lambda of X and lambda of Y should be same because isotopes will have, like, this is a plot which we have, so we'll get the same answer. And after getting a lambda, determine the half-life of isotope Y. So how to determine the half-life? So that is T half is equals to 0.693 over lambda. So T half is equals to 0.693 divided by lambda. So if we need lambda, 0.693 divided by T half. Or if we need T half, we have this formula. After getting a lambda here, lambda from here we'll substitute and we'll get the value for half-life. So the remaining part is related to graph. Like this part, finding that lambda is from graph, the gradient, and from gradient you will determine, if after getting a gradient, half-life is 0.693 over lambda, so you can determine the half-life. In question 4, a student used the apparatus shown to investigate the time taken for a hollow cylinder to roll down a ramp. H1 and H2 are there measured starting line. The student measured the height H1 of a start line from a bench using a meter rule. Two precautions you should take ensure that the result are accurate as possible. So what are the precautions when we are handling, like using using the meter rule or a meter scale? So we should look perpendicular first thing, or look perpendicular, avoid a parallax error. And the second thing, we should place a scale or a ruler close to it to measure the exact distance. So the ruler or the scale should be closer. That is one thing. And the second thing, we should look perpendicular, avoid a parallax error. You can also use a set square for that. Then the student measured the height H2 at a finish line, and she record the difference in the height between the starting line and the finish line, which is 65 millimeter plus minus 1. Uncertainty in change. Look, the how to work out the uncertainty. When we are working out the uncertainty in delta H, so how delta H is calculated? Delta H is calculated by using a formula H2 minus H1. So delta H, which is equals to H2 minus H1. And here we have to say why the uncertainty of delta H is 1 millimeter. Like when we measure it is, so what is the reason for that? It means whenever quantities are added or subtracted, the uncertainty always adds. If we are finding like any other physical quantity by addition or by subtraction, whenever we calculate the uncertainty always add. So it means the uncertainty in H2 will be, because we are using a meter, like a ruler is there. So it means the uncertainty in measurement of H2 will be 0.5 millimeter, and uncertainty in measurement of H1 is also 0.5 millimeter. That's why the total uncertainty in delta H will be 0.5 plus 0.5, which is equals to 1 millimeter. So you will refer here, the measurement H1 and H2 have the uncertainty of 0.5. That's why the total uncertainty in change in the height or delta H, which is H2 minus H1, should be 1 millimeter. Is it clear? So uncertainty always add even the quantities we are finding by subtraction or addition, but uncertainty always add. If a quantity we are finding by percentage, by division or multiplication, then we add the percentage uncertainty of each quantity and then find the total value. So why the uncertainty in delta H is 1? Because it means delta H is calculated by H2 minus H1. So H1 should have an uncertainty of 0.5, H2 also 0.5. That's why the total uncertainty will be 1. The student placed the cylinder on the start line and release, and she immediately started the stopwatch and measured a time for the cylinder to roll. She repeated the measurement several times. Calculate the mean value and its uncertainty. How to calculate a mean value? Remember one thing, if any of the value appear to be anomalous, like out of order, we'll ignore that when we are taking a mean. And how to take an uncertainty of a group data? It is a maximum minus minimum divided by 2. So to take a mean or average, they all appear in the same. So this will be 2.10 plus 1.86 plus 1.94 plus 1.89. And then we divide it by 4. This will give us the mean value, which is 1.95 seconds. Then what about uncertainty? Uncertainty of a group data is maximum value of the group minus minimum divided by 2. And again, if for example, if one of the values is anomalous, we'll ignore that. For example, if one of the value was 3.1, so we don't consider that. Even in average, we don't consider. Even calculating uncertainty, we don't consider. We only consider the values which are in a range. But in this case, they all appear in the range. So it's a maximum value, which is 2.10 minus the minimum value 1.86 and divided by 2. So this will give us uncertainty of 0.12 and the time was 1.95. Is it clear about the uncertainty and the average? So group data uncertainty is maximum minus minimum divided by 2. When the student made a ramp less steep, he reduces the value of H1. Explain how this might improve the measurement of a time. Look, student reduces this. When the student will reduce the H1, so the inclination or the angle will decrease. If the angle will decrease, it will take longer time. As it will take longer time, so as a result, because the idea is that when we calculate this thing is how this might improve the value for the time. So what will be the effect when we reduce the inclination or reduce the height of the ramp? So the time will increase as it will move slowly. So as the time will increase, as a result, the percentage uncertainty, because what is percentage uncertainty? Percentage uncertainty is uncertainty divided by value recorded into 100. So if we record any higher value or a greater value, the percentage uncertainty will be same. It won't make much difference, but the percentage uncertainty will decrease. So mark distribution here, you will mention it will take longer time as we reduce the slope and the time recorded will increase. So the percentage uncertainty will decrease. Two students each carried out this procedure for another value of delta H and they record the following for the same value of delta H. Compare the accuracy and precision of the data that each student has collected. So look, accuracy refers to if we are getting a right answer means we say accurate. But if we are getting like answer might be wrong, but it is like all values are closer to each other, it means it is precise. So when we compare as you can see, both of the students are getting a same average answer. So if they are getting a same like 2.44, so we can say student A and student B both are accurate. Like both are getting a same result about 2.44. But when we compare the precision, so both have the same accuracy, but we don't have a standard value. Like if we have a standard value, then we can say student A is accurate or student B is accurate. So first thing, both appear to be accurate because the values are closer, but there is no standard value given, so we cannot say the actual accuracy of the experiment. Like there is no actual value of a time given, that time should be like 2.45 second or 46 second. That is not given, so we cannot say the actual accuracy, but we can say as both are getting a same result, so it shows that both are accurate, but not about their accuracy with the true value. And student B has a smaller range. So as you can see, the range, like how much data has spread out. Student B, the maximum value is 2.5, and the minimum value, student A is maximum 2.5 and minimum 2.4. For student B, the maximum value is 2.48 and the minimum value is 2.40. So how much is the difference? That is 0.08. And how much this is the difference? 0.09. So student A is having a greater range of values as compared to student B. So we can say student B is precise. Both results are precise because they appear to be in order, but we have to compare their result. So the one which is having more spread out data, it means less precise. The one which is having a more cluster, like in a small area, we have more values, it means that is precise result. So the mark distribution here, you will mention both students have the same result, final mean and temperature time. It means both are accurate, but we cannot compare the actual accuracy as there is no standard value given. The second thing you will say, student B is more precise than A. And why is that? Because student B's data is less spread out as compared to student A. Then the relation between the time and the acceleration of a free fall is given by this equation, where S is a distance along the ramp. Start and the student record the following values. Time is there. Determine the value of a G. How to determine the value of G? You just have to substitute. Like G is your subject, so G is equals to 4S square T square delta H. So 4S is there, but because the units are important, S is in centimeter, so you should be able to convert into meter. When you are working out the percentage uncertainty, that time unit conversion is not important as you take a ratio. But when you are calculating a value, you have to convert the unit. So acceleration due to gravity is meter per second square. So this will be 0.8 square divided by T square, which is 2.44. In times the change in the height or delta H 43 millimeter, or 43 to 10 power minus 3. Then we'll simplify to get the value for G. So unit conversion is again important. That's why it's of 2 mark. 1 mark is for the unit conversion. So we get this approximately 10 will be there. Acceleration due to gravity, 10 meter per second square. Then determine the percentage uncertainty. Now look here in this one, see the quantities are divided and multiplied. So when quantities are divided and multiplied, you cannot add the uncertainty. What you have to do first, you have to get the percentage uncertainty of each of them and then add the percentage uncertainty of each of them. Because quantity, and if the power like square is there, it means the uncertainty will be 2 times. If cube is there, uncertainty will be 3 times. So as we are finding the value of a G is 4S square, T square and delta H. So if we find the uncertainty in S, the uncertainty and how to get, if you get the percentage uncertainty, how to calculate percentage uncertainty of a quantity? It's uncertainty divided by value recorded into 100. If we use the instrument twice, then uncertainty will be double. But here, as uncertainties are given, so we don't have to multiply. First, this is for the second part we are doing D2. So the distance so distance is equals to 0.1 uncertainty divided by value recorded. As I mentioned, when you're calculating a percentage uncertainty, you don't have to convert the unit. This will be uncertainty in S, but what will be uncertainty in S square? So that whole will be multiplied by 2. Because like if power square is there, it will be uncertainty will be twice. Cube is there, uncertainty will be thrice. If you are finding the uncertainty in T square, so uncertainty is 0.44 divided by value recorded into 100, but then again this whole will be multiplied by 2. And uncertainty in delta H, that is uncertainty divided by value recorded into 100. But we don't have to multiply this. Why? Because it's not square or cube. And after getting the percentage uncertainty of each quantity, so like example, this is 0.25%. The time square is 3.28%. And the change in height is 2.33%. So what we'll do, we'll simply add them to get the total percentage uncertainty first, which is 5.95% or 5.9%. So that was a question. We have to determine the uncertainty. 4, why we did not include 4? Because 4 is a constant. Like this constant will not have any uncertainty. But if sometimes they say, what is the uncertainty in 4s square? So uncertainty in 4s square, then what we'll do? 4s square means like s square plus s square plus s square plus s square. So we'll find the percentage uncertainty in s square and then add 4 times. So it will be like first multiplied by 2 and then multiplied by 4. So 5.9%, then deduce whether the value of a G is accurate. So what we do, if you want to calculate, we calculate two things, percentage difference with percentage uncertainty. Percentage difference, how to calculate a percentage difference? Percentage difference is maximum minus minimum. Actually, like you can also say this, the difference in the two values, standard and the practical value, the difference in the value divided by standard value into 100. That will give us the percentage difference. And percentage uncertainty we already calculated, which was 5.9%. So our answer, what is the standard value of a G? That is 9.8. Our answer was 10. So 10 minus 9.8 divided by 9.8 into 100. So this will give us the percentage difference. So when we calculate the percentage difference, our percentage difference is 1.9%. And percentage uncertainty. So if the percentage difference is less than the percentage uncertainty, if the percentage difference is less than the percentage uncertainty, it means the values are accurate. And if it was opposite, like percentage difference was higher than percentage uncertainty, then the values will be inaccurate. That's always a comparison. This is a very common question you will find in which you have to compare the two values.